Lesson 9.2, parametric equations and arc length. And what I did in this lesson is I wrote on every problem before I videoed because of all the lag and issues I was having as I was videoing writing. Parametric equations and arc length. So finding arc lengths of curves given by parametric equations: speed, velocity, distance, and arc length. So we know that parametric equations can be used to describe the path of an object moving in a plane. This leads to asking the question, how far has the object traveled? A particle moving along a curve in the plane with parametric equations, x equals f of t, y equals g of t, where t is time, has the speed given by these two formulas. These are formulas that you are going to want to memorize. Obviously, the formula on the left here is identical to the formula on the right because dx over dt is x prime of t and dy over dt is y prime of t. And obviously, you can pause the video at any time and write stuff down. We can find the distance traveled, which is going to be asked throughout this lesson. The distance traveled by the object moving along the curve between 2 points by integrating its speed. The distance traveled is the integral from a to b of v of t dt. Assuming the object never stops or reverses its direction as it moves along the curve, the distance traveled is the length of the curve, arc length. We've used this before when dealing with regular functions. So here's an example of what you've done already. This is nothing new. Example 1, an equation of the form y equals f of x. We're going from a to b, has an arc length L of such a curve is given by the definite integral below, which they're referring to this formula right there. Use the formula below to find the arc length from 0 to 3 for the function. Again, this is not parametric. This is just when you're asked to find the arc length. Recall what we did is we found the derivative, plugged it into that formula, and used the calculator. We are not going to have to integrate by hand. So over here, what I did ahead of time is I basically, here's f of x, I found the derivative. Remember, derivative means I bring the exponent in front and decrease the exponent by 1. And then I have to multiply by the derivative of the inside. That's what the 4 is. That's the chain rule. A lot of students forget that piece. In the end, there's your derivative. And you can look through, pause it, and go through my math. Then I plugged it into the arc length formula. There's the derivative. I simplified a little bit. 4 squared is 16. X to the 1/2 squared is x. And then all I did is plugged it into, I'm going to scroll down here. Maybe not. All right. Hold on, let me go forward a minute and then come back. There we go. And, okay. Well then, it is not liking me. I thought I'm going to go like this. There we go. And I plugged that into my calculator and got 14.25. That is the arc length. How do you plug it into your calculator? You're going to hit Math 9. Everyone's calculator is different. If you need help with that, please let me know. And I plugged in 0.3. I plugged in the radical 1 plus 16x, so you can test that on your own. And I got the arc length. So that is the length of the arc of the function going from 0 to 3. That is nothing new. We've done that. Now today we're switching gears and we're moving on to parametric. Arc length in parametric form. So notice arc length in regular form, it's just the square root, integrating the square root of 1 plus f prime of x squared. Now we're still integrating, but we have dx over dt squared plus dy over dt squared. That is arc length. So basically, we are integrating velocity. And the absolute value of our velocity is speed. The only difference, remember, between velocity and speed, which you know from physics, is velocity has direction attached to it. So that's a formula we're going to use. Here's our first example dealing with parametric. Randy the Roach is moving in the xy plane. At time t, his position is given by the parametric equations, where dx dt equals 3t and dy over dt equals t squared. Find the distance Randy traveled from 0 to root 15. So find the distance. Distance is arc length. So I'm going to use this right here. So let's see what I did. And there it is. So that formula right there. So I know what dx over dt is. It's above, and dy over dt. So I plugged them in. Doing a little bit of algebra here. You get 9t squared and t to the 4th. And I think at this step, I probably just plugged it into my calculator. And yes, I did. Just like I showed you, grabbing your calculator. I think I have this one on there. Yep, Math 9. There it's plugged in. And there was my answer, 30.192. So if I scroll down, 30.192 is the distance Randy traveled from t equals 0 to t equals root 15. Now, obviously, this is a video, so it's nice. You can stop it. You can rewind it. There's our first example with parametric equations finding arc length. Next example. Find the length of one arch of the cyclode with these parametric equations. So instead of using t, we are now using theta. It's still parametric because, again, that third variable is introduced. We have x, we have y, but we also have our theta. So the first thing I did, because it's saying find the length, so I know I'm going to find arc length, so I need to find a derivative, dx over d theta, which I did. This derivative of theta is 1. The derivative of sine is cosine. And I found dy d theta. So as I'm scrolling down, there's our formula. We're going from 0 to 2 pi. Because when we're dealing with the length of one arch of a cyclode, that is what it's going from 0 to 2 pi based on a unit circle. And now it looks like all I'm going to do, I'm going to actually take that away, is I plugged in dx d theta, dy d theta, and I went through the algebra. I expanded that out. Remember, this is a binomial, so you have to write it out twice. I foiled, and when I foiled, I came up with 1 minus 2 cosine theta plus cosine squared theta. But if you add that sine squared theta in, you notice that cosine squared theta plus sine squared theta is 1. So 1 plus 1, that's where I got my 2. Again, I plugged that into my calculator, and I got an arc length of one arch of a cyclode to be 8. Example 4. A particle is moving along a curve so that its position at time t, these are the positions at time t, x of t, y of t, where the position of x is shown in the graph. It says at the right, but the graph is below. For the particle, y of t, which is equal to xt squared. Find the speed of the particle at time t equals 1. So now it's not asking for the length of the arc or the arch or arc length. It's asking for speed. So we're not integrating. Speed is the absolute value of velocity, and this is the formula for velocity. So we know that, we look at this graph, it says xt is shown in the graph. So this is the graph. So if we want to find the derivative at 1, we're going to go to the graph at 1 and go up. And I can use what I know about the basics of slope, rise over run. So if I start at 0, 0, I'm going up 1, 2.5, and over 1. That gives me a slope of 5 over 2. That's where I got the 5 over 2 from the graph. dy dt, the derivative of that, I have to take the derivative of this. So the derivative of this is x prime t squared, but then the chain rule says I have to take the derivative of the inside, which is 2t. I now know that I need to find the derivative when t is 1. So I plug 1 in. 2 times 1 is 2. And I know that the derivative of or x prime of 1, I should say, is 5 over 2. And I plug that in. So now I know x prime 1 is 5 over 2, y prime 1 at 1 is 5. And I can now plug it into my velocity formula. And that's exactly what I did here. Went through the math of that. Pause that for a minute here. So this is dx over dt squared, dy over dt squared. And the speed of the particle at time t equals 1 is that. I'm going to go back a minute. Way back to here. Remember, speed is the absolute value of velocity, which is the formula that we're using. Example 5. At time t, the position of a particle moving in the xy plane is given by the parametric functions. Dx over dt, it's given, yt is given, so we need to find dy dt. That wasn't given to us. The function f of t is continuous and differentiable with selected values shown in the table below. Find the distance traveled by the particle from t equals 1 to t equals 5. Distance traveled means we're probably going to deal with arc length. So there's our table. So I know I'm going to need dy dt, and I did that here. So I know the derivative of this would be f prime of 2t, again, times the derivative of the inside, which is 2, times the constant. And it looks like, there we go, total distance. We're going to be integrating speed, and that is how we find the total distance, which is, in a sense, going to be the arc length. And I'm going from 1 to 5. So I'm going to plug in what I know, which is, I'm in the wrong spot here. All right. Dx over dt was given above. Dy over dt I found above. I'm plugging those in. If you square this 2, you get 4. If you square this, you get 12. What we know about like terms, this is f prime of 2t squared, f prime of 2t squared. We can add the constants in front. 4 plus 12 is 16. And now, if we take a square root of this, this is 4. Square root of this is just f prime of 2t. So So let's take this away before I can't. That's how I got to this step. And if I integrate this, if you integrate a derivative, you get back to your original, constant stays. By the chain rule, I have to divide by chain rule of integration, or it'd be like u sub in this case. You'd have to divide by the derivative of the inside, which is 2. And that's exactly what I'm doing there. So now I use the fundamental theorem of calculus by plugging 5 in for t and 1 in for t, and I get the values of the f of 10 and f of 2 from the table above. So I think the biggest piece that students might get confused on is this. Remember, when we're integrating a derivative, we get back to the original. If it was just f prime of t, I wouldn't be dividing by this, but it's f prime of 2t. If it was f prime of 5t, I'd be dividing by 5. And there we go. The distance traveled by the particle from t equals 1 to 5 is 12. One more example. At time t, the position of a particle moving in the xy plane is given by the parametric functions. They give us dx dt, the graph of y consisting of 4 line segments is shown. When t equals 0, the particle is at the point. Okay, this is where we need to understand what this means. It's at the point. I want to write something here. This is x, this is y. So that basically is saying that the position of x at time 0 is 4. The position of y at time 0 is 0. It's kind of going from rectangular coordinates to parametric coordinates. This graph reflects t on the x-axis and y of t on the y-axis, and that's important as we go through this example. I think I need to scroll up. I don't know what else is on this page. I don't think anything is on this page, actually. That is it. So we're going to go to the next part of the problem. We might have to scroll back and forth, though. Find the slope of the line segment, or excuse me, find the slope of the line tangent to the path of the particle. Slope, I want dy dx. And here's the formula of how I find it. So dy dt is, I can get from the graph. Let's go back and look at that. All right. So if I look here, when t is 3, that's why I'm going to 3, and I go up to the graph, there's my point. Well, the slope there, I can use what I know about rise over run. If I start up here, I go down to the right one. Again, down to the right one. The slope of this line segment is -2. I can find dx dt because I was given dx dt right here. All I need to do is plug in 3 for t. That's where I got this. So how do I find the slope now? Well, I have to take dy dt divided by dx dt. And I plug it into my calculator, and there is my slope of the line tangent to the path of the particle at t equals 3. Now we want to find the speed of the particle. Again, speed is the absolute value of velocity, which is this. Well, we already know dx dt and we know dy dt. Plug it in. And what I did is I just plugged that into my calculator. And after doing that, you get the speed of the particle at t equals 3. So we found slope of the line segment, we found the speed of the particle. Now we're going to find the position of the particle. This is actually, as I look through this, a really, really good AP kind of question. Open-ended, actually, on the AP test. We'll do more practice with it when we're spending those 4 days reviewing for the AP exam. Find the position of the particle at t equals 3. You want to understand this. This is a very popular question. The position of the particle at t equals 3 is represented by x of 3. So therefore, to get there, I know my starting position, and I'm adding to it my distance traveled to get to the 3, which is integrating. Think about it. I'm integrating a derivative. I get back to my original, which will give me this initial plus this will give me the position of the particle. So as I scroll down, I know that my initial, we know that from back here, remember, the initial, the x of 0, the initial position of our particle is 4. That was given to us. And we're integrating x prime of t, which again, I'm going to scroll back again, was given to us right there. All these were given to us. If you plug this integral right here into your calculator, you will get this number that I came up with, add it to 4, and you get the position of the particle at t equals 3. The last part, find the equation of the line tangent to the path of the particle at t equals 3. Point slope form, we know the initial position is 4. We know the initial position at y is 0. So we now know what am I forgetting here? Y minus, oh, I have to scroll down. It's right here. That's what I'm getting confused on. The position of the particle at 3, t equals 3 is this. We just found that above. And the position of the particle at 3 is equal to 4. And we can find that the position of the particle when t equals 3, y is equal to 4. We got that from the graph. And now we plug that all in, because they're asking for the equation of the line tangent to the path of the particle at t equals 3. We want to know and use x of 3, y of 3. And that's exactly what we did. That's it. This is a very good lesson, good video for the AP exam, especially this example 6. Take the time to understand the best you can, and I will answer questions in class.